Hi, my name is Joe Zhang, and this is my Lab 2 report on projectile motion. So the purpose of this lab is to compare experimentally and theoretically the position of a projectile position of a projectile affected by gravity and drag. And we use a crumpled up paper ball you see right there with 2.8 grams. Some key concepts that we need to know. Newton's second law, which states that the net force of an object is equal to the change of momentum over the change of time. This can be used to then plug into the velocity update formula, and then you can use that velocity to plug into the position update formula. Some further key concepts, we have the gravitation force, or the gravity force, the force of gravity, but this is near the surface of the Earth, which is shown by negative mg and then j hat or y hat. The gravitation force can be then used to, can be calculated using the formula g m1 m2 over r squared, where m1 is so you would plug in negative mg in for fg, and then you would cancel that out on the right side with m2, and then m1 would be the mass of the Earth, which is 6 times 10 to the 24, and then the radius is 6.4 times 10 to the 6th. And this will give us 9.8 meters per second squared. So we also have the drag force. Because air exists, it also inhibits an air resistance force that opposes the direction we move in. Think of it as air friction. In our experiment, drag force initially acts backwards and downwards, and then after the apex, drag force acts upwards and backwards, as you can see by this right here. Drag force is determined by the equation negative bv squared j hat, j hat. The system is the ball, and the surroundings is every element around the ball, from the air to the floor that it hits to the sound, everything. So some of the goals that we have and the assumptions that we made. So our goal is to observe and measure the position of the ball as it moves along the x and y axis, and compare it with the motion of compare the motion with two models made in GlowScript, one of which computes a perfect world without air resistance, and the other which computes air resistance. Assumptions: the components of the motions are strictly in the x and y axis and nothing in the z plane. So our procedure: first, we get a video of the ball being thrown in trajectory. Then we use a tracker app to analyze the position of the paper ball to get it at different times in the parabolic path. Then we use a GlowScript code to create a theoretical model of the paper ball being thrown, first without drag force, then with the drag force, changing the b value to mimic the trajectory of the experimental ball as closely as possible. And then we plot these data points all together on one graph to compare the models and outcomes. So here you can see how we plotted the points, and we have it over this many frames, and the delta is 0.033, as you can see, because it's 30 frames per second, and also it took 21 frames. So first, you can see on our left we have the x position, which shows a relatively straight path, which shows that the x velocity is not very affected, but as you can see, the y trajectory underneath is curved, which shows the how the gravity affects the ball. So first, we can calculate the initial velocity using these values up here. So we have delta x over delta t, delta y over delta t. You can just plug those in. And then also we have the initial position, which is given by x and y up here. And here you have the values that we then plug into GlowScript here. And then you can see how we put the initial vectors in up here. We have the delta t, which is 0.033. We have the ball's mass, which is 0.0028. And initially, since we're in theoretical context, we don't have any air drag, so this can be shown by b equals 0, and then we have the f net, which is just gravity, and then we have position and velocity update formula. Now when we have drag, now we have to incorporate a b value, which I found to be 0.0016, which worked perfectly. And then here essentially we have negative b v squared times the j hat, which is the vector. So we have negative b, and then this is the magnitude of the velocity squared times the ball velocity. And then here you can see that the f net vector is the gravity, and then also f drag, which incorporates above. Oh, my ball. And then everything else is pretty standard from before. So here we can compare them, and you can see that the y experimental went pretty much this far, and the y theoretical went further because it does not have any forces acting upon it, and the I with drag is a little shorter. And some potential causes is how, like, since we zoomed in so far to click on different data points, to click on different positions, maybe we could have hit like different like pixels on the ball, and especially since we had a white background and a white ball, it was more difficult, and also rounding errors. So do our models depict terminal velocity? Not really. This just shows how when it hit the ground, it kind of like flattened out. But in order to actually show this, we would probably need more time, more velocity, and more distance for it. So probably like dropping a ball from the stratosphere. And also, is the net force zero? No, net force is not zero. We have gravity, so it's always accelerating downwards. And if the object was thrown straight up, would it be different from if it was thrown at a projectile in terms of the time in the air? Yes, because the vertical component is only the sign of it, whereas if you threw it straight up, it would be the entire velocity going that direction. Thank you.